started. All right. Check the actual recording, and it is recording, so excellent. We got everything up and running. All right.
I have a goal.
So before we get into the heavy duty stuff that you all okay, let's talk about Ender's Game. Okay. Now, if anyone has not watched the Ender's Game nor read the book and do not want me to spoil the storyline, let me know and I won't talk about it.
I'm about to say, I'll just leave because you wanted to talk about it.
Have you watched it?
No, I haven't.
No? Okay.
So
What about this? Okay, so this is not going to be related to Ender's Game. Okay, this is just going to be League of Legends and some other online games that people play all the time. Perhaps even what is the game that red and blue is based on?
Halo.
Okay. So maybe even Halo. Okay. So first-person shooter game or your typical, strategic game and stuff like that. What if you're not really playing against another person that you think is just another person? Maybe you're playing against an AI. Okay. But the whole point is not for entertainment purposes. The AI is really trying to learn from playing games with people, to learn about strategies, to learn about being flexible, different ways of dealing with the same type of issue, and stuff like that. So at some point, that AI can be transplanted into a X47B, autonomous drone. So this way, it can react to real life situations and stuff like that. How can you be sure the other side is actually a person? It's actually a team of persons, right? People. You cannot. It's a Turing test, exactly. So you can probably tell by the misspelled words, okay? All the continuous, typing of WTF and so on. So you think, oh, that has to be another person on the other side, probably a 12-year-old or something like that. I know because my son played those games. So, so sometimes I watch over the show and I go like, okay. I cannot run the games that they play, so I don't get into League of Legends, just because it doesn't run well in Linux. But when I still had my Windows partition, I used to run Roblox, and in Roblox I play Base War with my kids. So I would sign in, and then you can. I usually just play a sniper in that game, and it's funny. I would have the they call those shieldies, because those are the people who spend a lot of their money to buy like the top level shield. The top level shield is useless against sniper fire. And I just buy a wetsuit and a sniper rifle. Yep, sniper in a Speedo. That's it. Anyway, so now you guys cannot get that image out of your head anymore. Yes.
Correct.
All right, so getting back to the boring stuff, I'm pretty sure hopefully you guys are somewhat, semi-awake at this point. All right, so the homework assignment. How many people check out the lab recording, the video recording from the lab session on Tuesday? Okay, so for those of you who have not checked it out, it is a good idea to check it out because I actually talked about the parsing part of dealing with a floating point number. So what we'll do today is, assuming that you have already parsed the number into the individual parts, how do we look at the value that is being represented and say, okay, now that we know this is the value, how do we turn it into the binary representation of a double precision floating point number? So that will be the focus of today's lecture. And obviously today's lecture is also getting recorded, so that's good, because if anyone needs to review it, we can now review it. So what we'll do is we'll start with a particular number, and I will go ahead and just pretend that I'm the program, and then we'll do the processing. Okay. So we'll pretend that we are starting with a string that says E, a 3, E, and then minus, 3. Okay, there we go. Okay. So would that be a legitimate floating point number? In base 10, okay, because it is 3 times 10 to the power of -3. which is otherwise known as 0.003, okay, or 3 billion something, right? Okay. So I'm assuming that you have either watched or will watch the video from the lab portion of Tuesday, where I gave you, a subroutine to at least recognize the digit portions of the number. Okay, you will still have to do some of your own parsing and conditional statements to see that, oh, there's an exponent component here, and oh, the exponent has a negative number. So you'll still have to figure that part out. Okay, so at this point, I will just make the assumption that you can turn this number into the following representation, which is not very far-fetched. Okay, it's not easy. It's not difficult to get to this point. So I'm assuming that you can get the number into a denominator, the numerator first, numerator, and you can get to the denominator also, denominator. Okay, there we go. So in this case, the numerator is just 3, okay, and then the denominator is 1,000. Is that making any sense? Okay. So I'm assuming that you can at least get to that part. At least you can parse the individual portions of a floating point number as a string and extract the mantissa in base 10 and also as well as the exponent in base 10. So we now have 3 as our numerator and 1,000 as our denominator. Okay. Any questions at this point? Okay. If there are no questions, then we'll say, okay, but how do we convert this into the binary format that we need? Okay, so normally, if I use integer division, 3 divided by 1,000, what is the answer as an integer? 0. That's not very helpful to me, is it? Okay, so what I need to do is to bump up the numerator as much as I can, okay, so that the division is actually meaningful to me. Is that making any sense?
Yeah.
Okay, all right. So I have the logic already uploaded into Moodle. I can clean it up a little bit. I think it's a little bit redundant. It's not incorrect, it's just redundant, okay? So what I'll do is I'm going to also keep track of an exponent of 2 as a correction factor, okay? So I'm going to say that this is the same, this is 3 divided by 1,000 times 2 to the power of 0 to begin with, because the correction factor is 0 to begin with. And I can smell a lot of cigarette smoke. I'm going to go outside and see what it is. Is there anything going on there? Something that I can see. All right. So what I need to do is to bump up the value of 3 as much as I can, so that the division will give me as much precision as possible. Is that, yep?
Is that 2 to the 0 power or XOR to the 0?
Sorry?
Is that 2 to the 0 power over there?
2 to the power of 0.
Okay.
I'm going to change the notation because this is also exclusive OR. So I'm going to use times as the exponent symbol. Okay?
Thank you.
Mm-hmm, sure. Or if you prefer power to 0, that's, which one do you like? Power or times?
Times.
Times? Okay. All right. All right. So if this is the value that I want to represent, I can double 3 to become 6, and then make my correction factor 2 times -1. Is that making any sense? Okay, because I just have to make sure they end up representing exactly the same value. I can make one bigger and then use the exponent to correct for it. Okay, so what I will do is I'm going to take this to the extreme. In other words, I will take 3 and try to multiply it by 2 as many times as possible, so that it is the largest possible value using the 64-bit representation. Is that okay? Yeah. So the question now is, how do I go about doing it?
How can we know the first number is 3 or 6? Or
Say again?
How can we define the numerator?
You have to figure it out by parsing the input string.
So if I can input any number, anything there.
That is correct. This is an example.
So, I mean, how can we, but because the first you have 3, so you use the power 0, and the second you is 6, you use the negative 1. But if I just have another number, how can we know the power should be? What's
Well,
the rule?
this one is divided by 1,000 because of the exponent of being -3 in base 10.
But the power, because we change the power to
power.
power 0 to power -1. I mean, if I got number is like 900, what would be the 2 power changed to?
You mean this part? If
Yeah,
the 3 is
second part.
900,
Second part.
this one,
No, the under you.
this
because-
one here,
Yeah.
this denominator cannot be anything other than powers of 10. Because it's only here because of the exponent of a floating point number expressed in base 10. So it can only be, 1, 10, 100, and so on. Cannot be any other number. It has to be a power of 10.
Power. Yes, but the problem is, my question is, how can we, for the program, because you got any number, you can get the second one, which is like power 0, power -1. If I just pass any number, how can we program this rule to know what the
Well,
power
that's kind of your assignment. I mean, you kind of have to put the components together. I gave you a subroutine that can take out the 3, and you have to kind of parse the e and the
Read
negative
the E,
symbol,
yeah.
and then you can parse out this 3 too. So from the 3 and the negative, you know this is 10 to the power of 3 as a denominator. Okay, but remember, you cannot use the power function as a floating point number. So without the floating point function to compute a power, how do you compute 10 to the power of 3? Okay, it starts with an L. No, log, those are all floating point numbers. A loop. Yeah, just a loop, right? Well, for those of you who prefer recursion, you can do it recursively as well. Okay, but assuming you want to do it with a loop, okay, so you can basically write your own power function. So with 2 integers, x and y. So this is the base, this is the exponent. So just write your own function to do it all in integer. Speed is not a big deal, okay? So don't worry about speed. This y, according to the restriction of the homework assignment, can only be up to 5, okay? So going through a loop 5 times, each time only involving addition and multiplication, is not a big deal. I'm pretty sure an i5 processor can handle that without overheating or blowing up. Okay, so there's no need to use the floating point number library for this purpose. Just write your own loop and do it the slightly less efficient way. Okay, all right. So if I take this all the way to the extreme, what is the representation of 3 times some kind of huge power of 2 that would use up all 64 bits? It's an unsigned number, okay? We're dealing with unsigned numbers here. It'll be 1, 1, and then, because 1, 1 is 3, right? So it'll be 1, 1 followed by 62 zeros in binary. Okay, so I'm going to write out that number, okay? But in hexadecimal, and even in hexadecimal, this is going to be a pretty long number. It's going to be C followed by 3 zeros. Okay, I have to break it up to actually count. Okay, 1, 2, 3, 4. Okay, there we go. So this number in hexadecimal, you cannot have spaces in between, by the way, because otherwise it will be, it won't be recognized. So this is the number that I want to represent, but there's a quick and easy way to represent it too. The quick and easy way to represent this, I'm going to leave this here just so that, just for amusement purposes. But this is really the same thing as this, right? 3 left shifted 62 times has 62 zeros padded to the least significant side with 1, 1 on the most significant side. So it's the same thing. A whole lot easier to write. Is that okay? Now, but because I am shifting to the left 62 times, I have to make this up using the exponent of 2, just so that I'm representing exactly the same value. Is that making any sense? So what would be the exponent of 2 in this case, just to compensate for left shifting the number 62 times? It's a magical number. It would just be 62, exactly. Well, negative 62 to be sure. Yeah, because when you multiply one side, you have to do the quote-unquote subtraction on the other side. But subtraction is just subtracting 1 from the exponent. So that's why the number of times you left shift is the negate that, and that becomes the power adjustment for the 2 exponent. Is that okay so far? Okay. And I can refine this even further, okay? Because 1,000 has a whole bunch of has a bunch of contiguous zeros on the least significant side. Okay, so that's just wasting space, right? Because I'm losing precision. I can be potentially losing precision by having a power of 2 as a factor in the denominator. So what I'll do is I'm going to make this even better, because 1,000 is 8 times 125. So 125 is no longer divisible by 2. So now I need to readjust my factor to what? Every time I have the denominator, how do I compensate for that with the power adjustment?
You would double it if you have the denominator.
No, I have to subtract again. Yeah, every time I right shift the denominator, I have to add 1, subtract 1 from the exponent.
Oh, because you're taking
Because
factor.
exactly, because I want to preserve the value being represented. So in this case, it is shifted 3 times. Okay, so if I don't take this out, I can say this is the same thing as that. Okay, so that's why this becomes negative 65. Are there any questions? So what I'm trying to set up is having the numerator to use up all 64 bits. And I will try to make my denominator using as few bits as possible, so this way I can preserve as much precision as possible. Are we still doing okay so far with this code? Or with this example so far? Is that cool? Okay, all right. So whatever number I end up with here, okay, which is this portion here, is going to be a pretty long binary number. It may or may not use up 53 bits. Okay, now 53 is a magical number, because remember, in a floating point, double precision floating point number, what is the number of bits for representing the fraction part of the mantissa? 52. Okay, but that's just a fraction portion. So that means there's also an extra 1 on the other side of the decimal point, or the binary point in this case. Okay, so that's why 53 is a magical number. Okay, so what I need to do is to really take a look at this number and find out how many bits it's going to use up, and how many most significant zeros do I have in a contiguous form. Okay, and as lazy as I am, I'm not going to do this by hand, right? So what do I do? I would use GDB, abuse GDB as a calculator. Now there's a reason why I use GDB as a calculator, because it understands C and C++ operators. That makes it very, very useful for that purpose. Okay? All right. So the first thing we'll do is to check whether it can deal with 64-bit numbers. So we'll do this. And it cannot deal with 64-bit numbers. So that means I can see if I can do this. Long, unsigned. Okay, that's better. Okay. All right, so I just have to cast everything to long, unsigned in order to do my calculation. So I can do just one cast, and the rest I don't need to cast again.
That variable number 2, that's the decimal representation, not hex, right?
This is a decimal representation. Okay, so that becomes my quotient. So that number, 110680 blah 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 blah, is basically 3 left shifted 62 times divided by 125. Is that okay so far? Okay. And that is not the number or the value that I want to represent. It is a part of it, okay? Because the correction factor is all the way here. This is my correction factor. In other words, I have to take this number, which is an exact number, and multiply it by 2 to the power of negative 65. Then I should have 0.003 back. Are we doing okay so far with everything up to this point? Okay. But I'm not too worried about the exponent part, okay? That part I can deal with later. Right now, I need to know how many bits are actually being used in $3. I like GDPs because now I can refer to the result. Which result are we talking about? Okay. So we want to take a look at the value of $3 and figure out, okay, but how many bits is it really using? So a quick and easy way to do that is to print it, but this time as a hexadecimal number. And there's a way to fill out all the digits, but I mean, let's see whether this, oops. Okay, this will do it. What I need to do is to do some counting here, which is going to be tedious. So we have 4, 8, 12, and 15. So it only uses up 15 digits, where we have 16 digits, with a 64-bit number. Okay. So what I will do is I will look at this number. The most significant portion, or I should say the least significant portion, is not important. So everything from the 8 all the way to the right-hand side, they are useful, but at this point, they don't concern me at all. Because when you look at the most significant part of a double precision floating point number, we have the most significant 12 bits. There are 12 bits here that are not useful for the mantissa. Okay, because we use up 1 bit for the sign, we use up 11 bits for the offset exponent, and this is the portion where the mantissa fraction actually is used. Okay, so at this point we have a 1, so we basically have a 0 here. Okay, the most significant 4 bits are a 0. The next significant 4 bits is a 1, which means it is a 0, 0, 0, 1 here. And so I'm not quite done with this yet, okay? Because I need to clear out 12 bits, where I only have 7 bits at this point that I cleared out. Are we doing okay so far? We have 1, 2, 3, 4, 5, 6, 7 zeros, but I need to have actually 11 zeros. Okay, not 12, just 11. Okay, so there's 7 here. I need 11. So the difference is 4. So what I need to do now is to shift it 4 times, right? Shift it 4 times, so that I have exactly 11 bits left. Okay. So let's go ahead and do that. But before we do that, we are going to also remember the exponent. Okay, so we'll go ahead and say, let's see. Okay, so this is what we'll do. I'll just copy and paste the number here. Copy and paste.
No, we don't understand. Why don't they 1,000 shifted right is 3? How did that work? 1,000 shifted 3. Shifted 3.
Because I want to remove all the contiguous block of zeros in the denominator.
But the value is 1,000 shifted 3 is 1, 2, 5. Is that right?
Okay, first of all, is 1,000 divisible by 2?
Yes.
It's 500. Oh, that shifted me.
Is it divisible by 2?
Yes.
I understand. That's a shift
Okay,
me.
and then is 500 divisible by 2?
Yeah.
Is
Yes.
250 divisible
Yeah.
by 2?
Yeah.
Is 125 divisible by 2? No.
I said, no.
So we stop at 125.
I see.
Yep. Okay. So we need to shift it 4 more times so that we have 11 bits, or only use 53 bits to represent the quotient, okay? So the next thing we need to do is now to take this number and say, oh, this is all good, but it's actually using up too many bits, okay? I don't need that many bits. So what we need to do is to take this number and say, let's go ahead and get rid of, what was it, 4 bits? Yeah. So we get rid of 4 bits here, but if I get rid of 4 bits here, I also have to adjust in the exponent. And this time, how do I adjust it? I am making the quotient smaller, so I need to compensate by adding to the exponent by 4. So negative 65 plus 4 is negative 61. So I'm doing all this game to move the bits around, but at the same time, I'm also keeping track of the correction factor using the exponent of 2. Are we still doing okay so far? Okay, all right. Okay. So when I look at this number, okay, this rather huge and messy number, it's going to take up exactly 53 bits. Now, why do I use 53 bits instead of 52 bits? Because according to the documentation, that 1 point, the 1 of the 1 point, is implicit. It is not actually represented. Yes?
Sorry, I'm a little bit lost. The first time when we shifted 3, which means the power negative 62 changing to negative 65. Is that right? The first shift 3.
When we shift it by 3, we have to correct for making the denominator smaller, and as a result, the exponent also has to be smaller.
Yeah, so the original is the power negative 62, so we plus 3, which is negative 65.
Yes.
And then we shifted 4.
Because we have too many bits in the quotient. I only want exactly 53 bits in the quotient, but I have what, 61? So 61 minus.
Is that 69 or 61?
Now we have
Is that 69?
yeah, we have 64 minus 7, which is what?
64 minus 7.
50.
50 something.
No,
Yeah.
4 minus 7.
Yeah.
4 would be 4, and then 3 would be 53. No, 57.
57. Okay, yes, it is 57. So we have a quotient of 57. Okay, let me just highlight which part is 57 bits. This is taking up exactly 57 bits. But I want something that is taking up exactly 53 bits. So that's why I'm going to shift it 4 times to get rid of 4 bits. Okay, I'm shifting it to the right. So I am losing bits in this process. But I really do not have the room or the space to store the entire quotient, so I'm going to toss some away. But when I toss those bits away, I have to adjust the exponent because I have to maintain the value that I'm actually representing. Is that okay? Okay. So now I have a number. Okay, if you look at the binary representation of that long hexadecimal number, it is actually representing 1 point and then a whole bunch of zeros and ones in base 2. There are exactly 52 of these digits, which is what we need. Is that okay? But there's one caveat to it. The caveat is the quotient actually has its decimal point or binary point here and not all the way here. So I have to correct for this as well. Is that making any sense? Okay, the binary point is implicitly here, but in the double precision floating point number, it has to be here. So I have to basically move the decimal point or the binary point in this case 52 times until it is here. If I move the binary point once over here, I am dividing the number or the value by 2. So I will have to increase the exponent by 1 to compensate for each position of shifting. Is that okay? And since I have to shift exactly 52 times, I have to add 52 to the exponent. So I'm going to do that here. Okay. So I will say
Is it because that's a fraction that a left shift
Yep.
relates to a division? Because wouldn't a left
Right,
shift normally
because
be
right shifting 1 is the same as dividing by 2.
Yeah.
Left shifting 1 is the same as multiply by 2.
Okay, but because that's a fractional part, it's actually division.
Yep. So what we end up with here is, I'm just going to copy and paste. So what I'm ending up with is an implicit 2 to the power of 52 in order to do the binary point shifting. Actually, this is a division. So I have to adjust the correction factor by adding 52 to it. 61 plus 52 is negative 9. Is that right?
Yeah.
Okay. yeah.
How can we shift
This
that?
is the kind of thing that I worry about. Okay. So, but the value being represented is still the same. Okay, that has not changed. Okay, let me just ask one more time. Does everybody understand why I'm dividing the value by 2 to the power of 52? Yep.
Shouldn't it be 2 to the negative?
Say again?
Shouldn't it be 2 to the negative?
No, but I'm dividing it.
Equal number.
Yeah, so.
Because every time I move the binary point over here, it is dividing it by 2.
Yeah.
So by dividing it by 2 to the power of 52, I'm moving the binary point 52 times all the way up to here. Okay? So we're pretty close now. We are actually pretty close to what we want. So the next thing we want to do is to take a look at, this number. Yep.
The only reason I said negative 52 was because if 2 to the power of negative 61 over 2 to the power of 52, then you subtract the exponent, so negative 61 minus 52.
Same thing.
You're dividing.
If you, well, you can change the division by with a multiplication, then it is negative 52.
Yeah. But if you, but alright, so are you saying it's 2 to negative 61 over 2 to the 52?
Okay, so the bottom line is this number, this value has to be preserved.
Yeah.
So if I change the power to
Okay.
negative 9, I have to compensate by dividing it by that power of 2, just so that this portion is going to be the same as this portion here.
I thought you were dividing the top.
Why do we need to do this one? It's the same as the last one.
It is the same, but
Yeah.
the implicit point of the floating point number is not here. It is all the way over here. So I have to adjust it by moving the binary point all the way over
Oh,
here.
you combine binary there and there.
Yep. Okay, so we're pretty close, okay? So what I want to do is to double check now. I want to look at this number and just to make sure that it is using up exactly 53 bits, okay? Not 52, 53, because the 1 point, which is implicitly represented in the double precision floating point number, still needs to be here in this particular format, okay? So what I will do is to copy it, paste it here, oops. Print /x, paste, and then I just have to do the cast once, long, unsigned. Okay, so it is this number here, which is not very surprising, because we just lost 1 hexadecimal digit, right? And if you count the number of digits, we have 4, 8, 12, 13, and 14. Okay, so it has 14 hexadecimal digits. Now, when you have 14 hexadecimal digits, and the most significant one is a 1, so how many binary digits do I need to store that number? The most significant hexadecimal digit is a 1, which means when you translate it into binary, it is 0001. The rest, I don't really care, okay, because they're just a whole bunch of zeros and ones. But how many are there over here? There are 13 of them, right? There are 13 hexadecimal digits, which translates to how many binary digits? 13 times 4, right? Because 1 hex to 4 binary, so that means there are exactly 52 bits, binary digits. Plus this extra one, 53. That's exactly what we want. So now we got the fraction of the mantissa done. In other words, when you look at the actual 64-bit double precision floating point number representation, we got this stuff done already. What is left is the exponent and the sign. Are we doing okay so far? The worst part is over. The worst part is over. Now we are just dealing with the easy part.
Is that sign we have to input a negative or positive, or if they don't have positive?
Can you ask that question again?
My question is if that sign for positive number we didn't put that plus there, is that supposed
If
to?
the value you're representing is non-negative, we put a 0 here. If it is negative, you put a 1 here. That's just 1 bit.
But when we input the value, we are not going to put a sign, is that right?
You can.
I mean, for negative number, we have to put a negative.
Yes.
But positive, we're not going to put that.
You can put a positive according to the syntax description. You can put a positive. You have to check for it.
No, I mean, for my program, if they don't put the positive, so should I just if
Okay,
it's
we'll
not?
get back to that one later. Okay, because the train is moving at a certain speed. I can't stop right now. Sorry. Okay, so now we're almost done. We just need to figure out how do we represent the exponent, which is only this part here. This part is not represented because the binary point is implicitly not here, but all the way over here. So that's why the highlighted portion on the projector is just there for the calculation of the exponent, but it's never really represented as a part of the actual exponent. Okay, that part is very important because because that is represented here just so that we can calculate the correct exponent. Okay, which is only -9. Okay, so -9 is the actual exponent. But if you remember when we review how a double precision floating point number is represented, the exponent is offset by 1023. So that means we have to add 1023. Okay. So the actual exponent represented, or exponent in the number is 1023 plus the exponent that we actually want. So in this case, that would make it 1023 plus -9, which is 14, I think. Right? 1023 minus 9 is 1014, I think.
Yes.
Okay. But that 1014 is going to use up the 11 bits here in the exponent portion. Okay? So that means if I want to look at, okay, so the exponent component is, in this case, 1014, left shifted how many times? The magical number, how many bits do we use to represent the fractional part?
50.
52, right? So this is the bit pattern, okay? This is the bit pattern to only specify the exponent of the double precision floating point number. Is that okay? We have only one extra thing to do. We have to get rid of this one here. We do. We actually do have to get rid of this one here. We know there's a 1 here in the 53-bit representation of the quotient. We just need to get rid of this one. So what is the quickest way to get rid of it?
Right shift.
No. You don't want to do any right shifting because right shifting will lower the precision of the number. We are going to be losing.
Subtract 1?
You can do a subtract, but it's not a subtract 1. It will be subtracting.
Oh, the whole, like it's a 7,
Yeah.
it's 11-bit representation.
Well, since we know there is a 1 over there, we can use bitwise OR. I mean, the exclusive OR. You can do a bitwise AND with a mask to mask out that only that bit. Yep. So there's a variety way of doing it. Okay. If you want to use the bitwise AND or using a mask to do it, this is the way to do it. Okay. To get rid of the 1 point of the binary mantissa. So what we'll do is we are going to take a look at this number here, paste it here, and then we'll just go ahead and mask it with the bitwise NOT of 1 shifted 52 times. So I'm hoping you guys still remember your bitwise operators. You still do? Okay, that's pretty good. So 1 left shifted 52 times is basically 1 followed by 52 zeros, and also has a whole bunch of leading zeros. So of the entire 64-bit number, only 1 bit is a 1. If I perform a bitwise NOT on that bit pattern, it just flips everything. So we end up with 63 ones, not contiguous, they separate into 2 chunks with 1 single 0 at bit 52 position. Yep.
Or bitwise operators supposed to be taught in 360 or 301.
Well, that's the way I taught it.
Well, none of my teachers taught it. So.
Okay, so if you're not in my class, I'll explain it quickly here. Bitwise NOT, which is the tilde symbol, is just exactly doing the NOT thing. Okay. So if you, so it depends on the width of the operation. So you have to be kind of type specific here. So if you are if you're doing a bitwise NOT of a 32-bit number, okay. So I'm casting this number to 32-bit first. So let's say this is I don't know 05. Okay. So what you end up with is a whole bunch of zeros, 101, but you're flipping all the ones into zeros and all the zeros into ones. So the result of this is going to be 0x f f f f f f f 8. Is it 8? Yes, it is. Yep.
Yeah.
Yep. So are you getting it?
Yeah.
Okay. But it is important to know what is the type that you're dealing with, because if this is 64_T, then we have a whole bunch more F's on the other side, because all those zeros are actually represented. If this is a 16, then it becomes just FFFA. Okay. Is that okay?
Yeah.
Just a really quick brush up.
I got it.
Okay. But in this case, I will type up the entire thing here, long unsigned here, and this one also needs to be casted. Now, not every single number needs to be casted to long unsigned, only the ones that has to do with a long shift operation, because otherwise the default assumption is an integer is only 32-bit wide, and with a 32-bit number, if you shift it more than 32 times, it's all gone. There won't be anything left. So that's why when you're shifting it more than 32 times, you have to tell the compiler, or in this case GDB, that we are dealing with a 64-bit number. Keep track of all 64 bits.
Would it be wrong to mod it so that your shift, like however much you want to shift it by, you mod it by 32 so that
you can mod it, but if you mod it, you won't be modding it with the mask that I'm using here. You'll be modding with another number. So there's a variety of way to get rid of that one single bit.
but it won't come up with the wrong answer.
It won't kill it. That is correct. Yep. Okay, so now we have a pretty long expression like this one, and that's just the fraction of the mantissa. So we'll go ahead and specify the other portion. So we have all the components already. We have the exponent, and we don't need to deal with the sign because this is a non-negative number. It is just plain 3, right? Okay, so we now have the entire bit representation of this number. The entire representation, so this one needs to be casted as well, long unsigned. Okay, there we go. So what we'll do is we will now combine this particular bit pattern with this particular bit pattern here, and that should be the bit representation of a double precision floating point number that is simply representing 0.003 in decimal. All right, so paste, and then do a bitwise OR, okay? Because this is only going to specify the 11 bits for the exponent, and then the other expression, which is this part here is going to specify the. I'm going to put extra parentheses around it because it has a bitwise AND in it. So just to be sure. All right. So when I press the Enter key, that's the bit pattern for a 64-bit double precision IEEE floating point number representation of just good old 0.003. Next question. How can we be sure that really is the case? How do you check? That's just 0.003. I can't do the cast here because whenever you cast, it will actually take the value in integer in unsigned format of this number and convert that one into a floating point number. It will convert the value itself, not just look at the bits differently. Okay, so we'll need a place to store it and then use the pointer trick to do it. Yep.
And then go to that location.
Yeah, unfortunately that means I have to kind of just take this number and then get out of GDB, put it back into a program, initialize a 64-bit number, and then get back into GDB and do the other trick to do it. Well, we can use printf too. Okay, so copy this. Okay, because I need to put it here, just to remember what it is. And nope, it's this one here. Okay, so we'll get out of GDB. Everything is being recorded, so don't worry about losing anything. And we'll go to the 10 folder and create a program called double.c. And we'll have, I need to do this too, include stdint.h. So this way we can spell out the type of an integer and how long or how wide the integer is going to be. This is going to be unsigned integer 64_t. I call it x. X is initialized to the number that we just dealt with, which is this one here, and return 0. Okay. So the purpose of this entire program is really just to store that particular bit pattern into a space that has 8 bytes. And then I'll use GDB to say, take the address of this variable and then cast the address into a double pointer and then dereference the double pointer so that we can look at the same bit pattern but using the interpretation of a double precision floating point number. Is that okay so far? Okay. All right, so let's go ahead and do it. gcc-g-. I'm just going to shortcut the whole thing and not go through the compiling step as a second step. GDB double, break the main program, run, single step. Okay, so now we can say print x, print /xx, okay, print it in hexadecimal, make sure that's the same number. So this is the moment of truth. Print the dereferenced version of a double pointer, which is actually just casted from the address of x, which is a 64-bit number, 64-bit unsigned integer. Okay, so I'm not sure I'm ready for this because everything leading up to this point, I think I did it okay, but I'm not 100% sure. So let's press the Enter key, and it is pretty darn close. Wait, how can it be pretty darn close and not exactly 0.003? I mean,
It's a computer.
because just like in 1/3 cannot be represented in base 10, 0.003 cannot be represented in base 2 without recurring patterns. So that's the tricky part, okay? Is that okay so far? So it does work. The method does work. So the next question is for you guys to answer. How do you code it? How do you write a program to do exactly what I did? Okay, so let's go ahead and revisit. Okay, let's go ahead and revisit what we have to do And then I just want to kind of briefly mention what kind of mechanism is available for you guys to use. And I assure you, there's nothing complicated here. Everything is really just conditional statements, loops, comparison, multiplication. Well, not even multiplication. We only have shifting. We do have one single division. Okay, division only happens once because there's a whole bunch of shifting taking the place of divided by 2. Let's see, what else do we have? We have certain additions. Okay, we have increment and decrements. We have initialization. We have a single addition of 52 because of the binary point having to shift to the left-hand side. That's it. That really is. Those are all the components. It's just making them in a structured way to get it to work. Right. But before we move on, I just want to see if we can print 0.3 without losing the decimal point. So it can't do that either. Yeah, you can see that there's no way to represent exactly 0.3, even if I just say print 0.3. Okay, you cannot do it.
Would printf doesn't have like an ability to we have an avoidable. So couldn't we?
Yeah, printf cannot do it.
Couldn't we could dash G because if you do dash G, you'll
Oh, not man, help. Okay, printf format string and then arguments. So printf percent G, you said?
No, I think no. It's like it's gonna be %I, but you got to use a qualifier in the beginning. So you'll want like.
Yeah, this is rounded.
Yeah.
It's using rounding, and that's why the portion that we missed is not represented here because it's already rounded. Okay. So are we ready to go back and kind of retrace all the steps just to make sure that we can kind of code it into the program? Okay, so let's go ahead and take a quick look at, it's only this long, it really is. Okay, the first part, which is not entirely easy, but it's just tedious for the most part, is to get the number that you want to represent into sign, numerator, and denominator. The numerator and the denominator, they have to be unsigned numbers, okay? Unsigned integers. They cannot be floating point or double, type, just unsigned numbers. And then you use an extra flag to say, okay, is it negative or positive number? That's the easy part. Okay. So once you get it into a numerator and a denominator, and I would just use 64-bit numbers for the entire thing, okay, so you don't have to worry about it. So once we get it into this form, the next thing we want to do is to say, okay, but how many times do we have to shift it so that the numerator will take up all 64 bits to represent it? Now, this is, of course, assuming the numerator is not a 0. Okay? If it is a 0, there's a quick answer. Okay? Because 0 is the same whether it is a 64-bit integer or a double precision floating point number. If you give it 64 zeros, it is representing or interpreted as the true value 0. Is that okay? So 0 is a special case that you don't really have to worry about. Okay. So you have to kind of figure out how many times you have to shift in order to use up all 64 bits to represent the numerator. Yep.
So for that one, we can look at it as 3, like the minimum representation for binary would be like 1, 1. So we need an additional.
But when you look at it from the perspective of the program, it doesn't really quite know how many bits it needs in order to represent that value. And you cannot use log, okay? Because log is the only way you can tell quickly how many digits is it taking. So what you do is you use a loop, right? So you use a loop and you keep shifting it until you use up all the bits. So now the question is, how do you know it's using all the bits? Well, you look at the most significant bit of a 64-bit number. If it is not a 1, you're not done. Keep shifting. But every time you shift, you also have to make adjustment to the exponent because you don't want to change the value that you're representing you're just shifting the number so you have a much bigger denominator, so that when you do the division, your quotient has a higher precision. Is that okay? Can I leave that to you guys?
So which means we have to check if the which is have to be 1, which means we move to the last digit.
Okay, I'll say this once because it is really a part of your homework assignment. Repeat, left shift once, and add 1 to the exponent. Is it adding? Subtract. Subtract 1 from the exponent until the most significant bit of a 64-bit number is a 1.
Which is 64
Can't be a
bits.
0.
Hmm?
It can't be a 0.
Exactly, because a bit can either be a 1 or 0. So if it is a 1, it is not a 0. So you want to keep shifting until it is a 1.
Exactly.
What?
No, I'm saying that because
No.
I think you went like it can't be a 0 because unless the number requires 64 bits, then the leading 64 bits are going to be zeros, right? Or they're going to be ones.
Because of the restrictions I place on the input itself, you cannot have a numerator that is too big.
Yeah.
So you almost
Okay.
have to do the shifting. Yeah. Because I restricted myself to only have 4 places after the decimal point, and also the most positive exponent is only 5. So the worst thing you can deal with is, like 10 decimal digits or something like that. Okay. And then with a 64-bit number, it can handle up to like 18 decimal digits or so. Yeah. So I'm almost sure that you won't hit, the problem.
Yeah.
Okay. Okay. So the other thing is you want to remove all the contiguous zeros on the least significant bit side of the denominator. Okay. Because 1,000 is divisible by 8, which implies it has 3 zeros at the least significant side. So you want to remove all those just so that you have more precision when you get to the quotient. So in this case, it's kind of the opposite of what we just did. Okay, in this case, you're checking whether the least significant bit of the denominator is a 0 or not. If it is a 0, do a right shift and adjust the exponent, and then go back and check again. I just kind of spelled out the loop for you. You just have to convert it into bitwise operations. All right. So once you're done with those 2 steps, then you end up with, a pretty big numerator, a smaller, but sometimes you cannot change it. Okay, sometimes, almost for certain you can change it, because it is always a power of 10. Okay, so it's almost for certain you can change this one, but it'll be smaller. Okay, this one will get smaller and smaller, and don't forget to keep track of the exponent. You do not keep track of this number. You just keep track of the exponent itself. Is that okay? Any questions at this point? The next step, this one is really just me going through GDB and come up with the actual representation, which is not a bad idea when you're coding, so you can basically check whether your program is working or not. Okay, just to double check. And then the next step, which is this one here, is to take a look at the quotient. Now, this is only representing one scenario. This is representing the scenario when the quotient is taking more than 53 bits to represent. So we're lucky, okay? Because the quotient has too much precision. We're going to have to lose some of the precision to limit it to only having 53 bits. Okay, that's the easy one. But you might end up with a scenario where the quotient is not using enough bits. That's possible as well. If it's not having enough bits, you pad bits from the least significant side until it uses up exactly 53 bits. So in that case, you'll be shifting in the other direction and adjusting the exponent in the opposite direction as well. So the bottom line is we want the quotient to use up exactly 53 bits. If it's using too many, we lose the least significant bits. If it's not having enough, we pad least significant bits and push the bits to the left-hand side until it uses up exactly 53 bits. Okay. Is that okay so far? And once again, you have to use a loop to do it. Okay. So depending on which scenario you're in, you either have to say while bit 52, okay, because we come from 0, while bit 52 is a 1, keep shifting it to the right-hand side. Okay, but you have to be careful because if you shift it one more time, then you lose the bit that you actually need. Okay, if it doesn't have enough bits, then you do the opposite operation. Then you say while bit 52 is a 0, do a left shift and adjust the exponent. Okay, so there are two scenarios in this case. You have to kind of decide which way you have to go. Are we still doing okay so far? Yes.
Is that 52, which means another portion? So of this side, if we have value there, are we going to, if the 52 is 0, but 50 0 is a 1, are we going to move shift left or?
I want bit 52 to be a 1 and no more significant bits to have a 1.
When we input the value, will that
Okay,
be
I'll draw the picture.
certain number?
That's the 53rd digit, right? That's the 53rd digit.
Yeah.
Well, we come from 0, so the
Yeah.
least significant bit is bit 0. So bit 52 is actually what we
1
call
0.
the, yeah. Okay. So if we look at the bit, if we look at the bits here, the last or the most significant bit is bit 63, 62, 61, 60, da da da, and then this is bit 52. Okay, I want the form to be like this. This has to be a 1. Has to be a 1. Okay, all of these they have to be zeros. I don't care what is on this side. Yep.
That's on the exponent side? That's on
Yeah, this is the
yeah.
exponent and the sign. Okay, and that's why well, this technically is a part of the exponent too.
That's what I wanted.
But we are going to lose this bit by the bit masking.
Yeah.
Yeah. So when you're just dealing with that portion, the portion that I'm highlighting, this is what I want. This is what that step needs to end up with. All right. The next step is easy. Add 52 to the exponent. That's why I said there's one addition of 52 as a constant to the exponent, and that's just for adjusting the binary point to the right place. Are we still doing okay? All right, so now we have, once we have this particular representation, which is this one, okay, so we're still looking at the same bit pattern. We want to get rid of the most significant bit, which is bit 52. So bit 52 is the only one that I want to clear, and this particular equation will get rid of it. Okay, so that takes care of the fraction of the mantissa of the number. The exponent is just going to be this number here. It's 1023 plus the actual exponent that you want to use. Okay. So what we do is we take this number and we shift it to the left 52 times, just so that it clears the entire fraction part of the number, and we'll use up these 11 bits for the exponent. So from bit 52 to bit 62, we'll be using it for the exponent. Now, because of the restriction I have placed on the input, you don't have to worry about, oh, but what if I need more than 11 bits to represent the exponent? We're not going to come even close to that limitation. And then the last one is the sign bit, okay? So if the number is a negative number, you just put a 1 at bit 63. Otherwise, leave it 0. Are we, yep?
Just out of curiosity, what's the biggest exponent you have without needing to have more space for the exponent side?
Well, we have 11 bits, right? So with 11 bits, we can go from 0 to 2047. But since this is already offset by 1023, right? So that means we can go from negative 1023 to positive 1024. So 2 to the power of 1024 is the maximum in terms of magnitude. And this is way beyond the range of numbers that we're going to deal with, because there are approximately 3 digits to 3 binary digits to 1 decimal digit. So if you, even if it's 4, we are dealing with a decimal number that has 100 places. So that's way beyond what we have to do. Yep.
I'm sure you probably already explained it, but what's the reason again that we're shifting it over 4 places up?
The right shift by 4
yeah.
to make the quotient use up exactly 53 bits to represent. Because this one uses up too many bits, and I want to reduce the number of bits in the quotient so that it will fit within 53 bits, including the 1 4. Okay. Yep.
What happened to deleting deleting 1 in the most significant bit because it's implicit in the string?
Because it is implicit.
Right. But where
Which
did that-
part does it?
Where did that go? Yeah.
Where is that code? It is right here. It is the bitwise end of a kind of big long mask.
Okay.
Yep. So that's basically getting rid of bit 52 itself, because I start off with a bit mask with only bit 52 on and everything else off. But since I first performed a bitwise dot to that number, so that flips everything, right? So that means I have 64 digits. Only bit 52 is a 0, and everything else is a 1. But if you do when you do a bitwise end with 1, you're preserving whatever you have originally. But when you do a bitwise end with a 0, you're clearing that bit. So that means we're only clearing bit 52 in this case. Yep.
So, from what I understand, the reason we can't express 0.3 is because when we do this, it's too big and we have to cut off bits at the end.
Yep. Yep. There are many numbers where we think we can represent, but it cannot be represented in base 2 exactly. Okay, because we only have 32 bits to represent the fraction of the mantissa. So even if you add the 1 point next to it, which is 53 digits, if you have a recurring pattern, it still cannot be represented exactly. It's just like with 1/3. Okay, so if you think about it, 1/3 in base 10 is what? 0.3, but the 3 is recurring, right? So that means when you usually write it's 3, 3, 3, 3, and depending on how many digits you want to write it, but there's a limitation. Think about 1/3 as a value, but this time you're representing it in base 3. So what is 1/3 in base 3? Hmm?
0.1.
Okay, so 1/3 in base 3. Okay, this is how we do it. It is 3 to the power of what?
-1.
-1. Okay, so there's one of these, right? And none of the other ones, right? That means it is a 0.1 in base 3. But that's exact. If you write 0.3 in base 3, it is representing 1/3 exactly. There's no recurring. But in base 10, it is recurring. So it has to do with what base you're dealing with. So in base 2, many numbers are recurring. Even 1/5 is recurring, because 5 is not, right, 5 and 2 are both prime numbers. That's basically the bottom line. So is that okay? Does that kind of help explain? Okay. Right. What about 1023? Can I represent 1023 exactly using this representation?
Okay, so what is 1023? That is like 2 to the.
Well, 1023 is a fun number because 1023 is 111111111.
How can you get that? fast.
Okay, 10 ones.
Yeah, because it's 2 to the 10th power.
Because it's 2 to the power of 10 minus 1, so we just end up with 10 ones. Okay, so the question is, can this be represented exactly using the format that we're dealing with? And the answer is yes. It's actually pretty easy because we just think about, oh, we just put a point here, and then we have to multiply it by 2 to the power of 9, right? So the mantissa, or the fraction of the mantissa, would be a whole bunch, 9 ones, and then a whole bunch of zeros. The exponent is going to be 1023 plus 9, which is 1032, okay? And that's it. So if you hard code this into the bit pattern and then convert it using the typecasting of the pointer, it will be coming back as 1023 exactly. What about 0.25? Can 0.25 be represented exactly using the floating point representation? 0.25 is 1/4. 1/4 is easy, right? It is just 1 times 2 to the power of -2. Hey, we can easily turn that into this, right? In fact, if you look at SAE units, okay, if you go to Sears, okay, go to the wrench section, go to the SEA version of all the wrenches, any one of those values can be represented using the floating point number because they are all based on what? Fractions that has a denominator of a power of 2. Well, I mean, you can only extend it up to a certain extent because if the power of 2 is more than 2 to the power of 52, then we won't be able to represent it exactly. But I don't think that wrench exists at Sears. What is the highest precision that people use when they specify the size of a wrench? I know there are 8ths, there are 16ths, there are 64th, there are 1/28ths. So 64th is the last one. So that only takes up what? 6 bits. That's it. Okay. All right. So are we doing okay so far with this stuff? So the way I describe it in today's class is actually more concise and more effective than the written version in Moodle. The written version in Moodle has some extra steps. It's not wrong. It is just kind of more tedious, and certain things can be combined.
Well,
You have a file in Moodle?
No, in Moodle there's a
Yeah.
link. It just made the link here. It's called n/d to double or something
Is
like
it
that.
under the
When you
non-integer?
upload this to
Right?
there as well,
No, it's under non-integer,
Yeah.
it's the second link. n/d to double conversion.
when you upload this file to there as well.
Okay.
Or
Sorry?
I like
when you upload this file,
Yeah.
This file?
because this is very useful, we use a lot. Yeah.
Fine.
Maybe just a link.
Copy, paste.
That's easy. Save us a lot of time.
But that's not my job. My job is not to save you time. My job is to make you learn this stuff, which sometimes requires using time.
Yeah, we can sometimes read more material, study more.
I don't know about that. I don't know about the part about studying more.
I mean, got more information, study get better.
Well, I can actually tell when and why, and well, not why. I can tell when and how frequently people go to Moodle and check the notes.
You mean
Sometimes
by
it's a little bit disappointing. Just put it that way.
by student ID?
Hmm? No, I have a complete log of everything. Moodle keeps track of a complete log. When you click on what item in the class. So, but I don't use my time to play Big Brother. Only when there are suspicious cases, then I'll do that. Then
You
go
can just
like,
generate a report and read it by student ID. You can just have a report by student ID.
okay, save. Okay, now you have the entire text document. But the document itself is not helpful, okay, because it does not explain what I'm doing with each step. So you have to combine that with the audio, at least the audio recording of this class to understand, oh, so in this step, tag is doing da da da. So reading the document itself is like, there's no point in doing that. Okay, what might be more helpful? Okay, so this is one way you can help yourself to study for this material, as well as get your program going. Is as you're watching the video the first time, make a little index. Okay, kind of a little index and say, at what timestamp tag is talking about correcting for what. Okay, making the denominator as small as possible, but without losing significant digits, or making sure the quotient is using up exactly 53 bits. Okay, so this way, if you only have questions about a particular thing and everything else is like, oh, I got it the first time, you can just watch that portion again when you're coding, and you don't have to search the entire 1 hour and 20 minutes for only that portion. So you can index it and just look up in your own index and go like, oh, okay, I know exactly where to find that. Which is also something you can do during class. It's like, oh, jot down the time. Yep.
Okay, so after all that, I'm gonna ask a really silly question. So when we want to store that, after we've gone through that process, and we end up basically with the hex number that represents the full thing.
Well, the hex number is one representation of the bit pattern, the 64-bit bit pattern.
But
right.
then when we get that, all we're gonna to store it is
To return it.
Is to just return it.
You just return it.
Okay.
You just return it, and then main will take care of the rest. Yep.
Okay.
So all you have to do is to convert the string into the bit representation of the double precision floating point number. And then you return the 64-bit integer just the way it is, and that's all it takes.
So
because
I'm sorry. So in main, do you mean like in main we'll have some variable x that's meant to store that, and we'll say it's equal to our function?
main is going to use the same trick that I did earlier. It will basically use either the typecast or the union trick. That's up to me to use, because you guys don't really have to mess with main for the most part.
Oh, because we don't have to write a main.
Right, you don't have to write main. Now, what you can write if you want to check your answer is this particular subroutine, and I'm just writing on the whiteboard. Okay, so you might want to write something like this. Okay, this is the only time when you can use double. Okay, not for calculation, just for casting purposes. Okay, so you just say this is I don't know how you want to call that. Okay. Guess what the rest look like?
Return that.
That's the only subroutine you can write that actually touches double. But it's going to be helpful because this will allow you to check whether your program is working or not. And I would use simple numbers to test it first, like 1. I'm not kidding, just use 1, okay? And you might want to separate your program into 2 halves, one half to do the parsing, and the other half to do the conversion. Okay, you can check the conversion part first, okay? You can even do that part first without the parsing, because you can just say, let's assume the numerator is a 1 and the denominator is 1,000. Okay, so I'm trying to represent 0.001. So you can check that and actually go through GDB, make sure that your conversion part is done correctly first. Then you can go back and do the parsing part, and the 2 parts can interface through the numbers numerator and denominator. So this way you can check your program and debug your program in parts instead of writing the whole thing as one single long subroutine, which will be kind of difficult.
Can we call another program, create a several program or functions, and just call them?
Say again?
I mean, because we have a different component there, we can create a function or
You can call
sub-program.
subroutines that you write.
So we can also write another program. I can call program as well. Is that right?
Call what program?
You can
write your own function, and in ATOF, you can call your own functions. So that would encourage hierarchical programs and making sure that you separate parts of the program into individual parts and stuff.
But we can also call another program and return the value if we want debugging more easy because functions under one
For debugging
file.
purposes, you can do whatever you need to debug your program.
One submit have to come back to that one file, is that right?
You can consult anyone too to write your program. I was just about to say something that's politically incorrect and I just cut myself in time. So that's good.
So this is more of like just an esoteric question. So
Okay, go ahead.
the other time you mentioned union,
Mhm.
and I ended up looking it up. I talked to Daniel a little bit, but so for this, if we
Union basically is doing the same thing as this, except it is quote unquote a proper way to do it.
because would you have time, or is that something you would do in lab?
Yeah, sure, I can do it. Okay, so let's go back to the program that we worked on, and we'll just do a union method. Okay, so we'll how did I call that program? Double. There we go. GDB, interestingly, also understands what is a union. Okay, so we can say union, X, and you basically define members of a union kind of the same way you define a struct, but the meaning is entirely different. Okay, so in this case, we'll say int 64 T I. This is the integer part of it, and double D is the double representation. So what's happening is it's using the overlapping space, okay, the same number of bytes for all members. So you can use one member to put things into it, and then use the other member to get something out of it. But it's not the same thing as a type cast. It's not casting to a double. It's doing the actual trick that we use here. It's basically using the same bit pattern, but interpreting the bit pattern differently. Yeah. So this is really kind of interesting because now we can say, instead of using X here, okay, I'll just be consistent and use uint here. So now I can say, union x, okay, lowercase x is the variable which is a union. But you can no longer assign to x all by itself because it's a union. So you have to say x dot I gets this particular pattern. So I'll just go ahead and compile the program the way it is. Oops, B main, run, single step. So now I can say, print x dot D, and it will print it out in the floating point representation. So it's basically looking at the same bit pattern, the same zeros and the same zeros and ones, but it's interpreting the 64 zeros and ones not as a single unsigned integer anymore, but this time as a double precision floating point number.
And we could do we could kind of use that to brutally kind of check certain numbers just to see what value our program should kind of return.
You can do that, but it still requires the exponent and stuff like that to be in place exactly. So there's not really a whole lot you can do in the intermediate steps, but you can use the bitwise operations at least to check. Okay, do I have a 1 at bit 52? Because that really is a very important step, is to make sure your quotient is only using exactly 53 bits, no more and no less. That is a very important step.
And we should not have one at 50.
Right. Now, then you can play with the exponent. If you're off by 1, you can kind of tell, right? Because if the number comes out to be 0.0059 something, then you know that you are missing the exponent by 1. Okay. So some of those errors will be kind of obvious and you can fix it easily. But if this number is entirely off, it's not even close to anything related to 0.003, then you have something else that might be wrong. Because if you're only off in terms of the exponent, it will be 0.03. It will be 0.003 times some power of 2, either on the positive side or the negative side.
Yep. What would happen if you use 52 bits for a number for 0.3?
Huh?
What would happen if you use 52 bits instead of 53 bits for a number like 0.3?
for 0.3?
Yeah, like if you use like you know how 0.3 has more precision than we have room for.
Mm-hmm.
What if we used 52 bits instead of the 53? Like we shifted it.
Oh, okay, I see.
Over.
Then you won't end up with that problem, but you can. But if you only shift it to 52 bits for the numerator, right?
Yeah.
So you're basically saying, for the numerator, you don't want to go all 64-bit. You only want to go for 53 bits. But then you can potentially losing precision, because what if the denominator is a larger number? So you kind of have to adjust for that too. So I would just kind of maximize the numerator and get rid of all the excess bits that I cannot store, and do it that way. Okay, any other questions? If there are no questions, I'll be over at the lab, and I'm hoping some of you will try to get started, early. And you can work on the parsing part first, you can work on the conversion part first, either one is okay. It's just that plan to spend time on this program.